Hi folks, today is the theoretical justification of our previous problem. Let me first recap what is the problem. Suppose I am a coffee lover and today I just have $1, $1. But each cup of coffee takes me a uniformly random number from 0 to 1. The question is, how many cups of coffee can I have today? And to solve this question theoretically, we only need elementary probability. So if you have this kind of background and you are also interested in the theoretical justification, we can start now. Using probability language, price of each cup of coffee is independently uniformly distributed on 0 to 1. And the total cost for the first n cups of coffee is of course the sum of xi till n. If we cannot afford the next cup of coffee, then we call that is our bankrupt time. It means the first n such that Sn is greater than 1. We can use mathematical notation to denote this bankrupt time. Mathematically, this thing is the minimum natural number such that S of this natural number is greater than 1. And we can notice two things. First, n is a random variable, which means n is random because Sn is random, the price is random. So the goal is to compute its expectation instead of compute its exact value, because for each time of experiment or for each day, this n, this capital M, is changing. It is random. And secondly, we can also notice that n is integer valued random variable because it means the cups of coffee. So we can use this, the below expectation formula for the discrete random variable. The thing remains to compute this term. The probability of capital N equals to some cup, the k cup. Now we have to compute it. Let's start with n equals to 1. If capital N is 1, it means we can afford the first cup of coffee. Recall that the cups of coffee takes uniformly random number from 0 to 1. So this thing must happen. We must afford 1 cup of coffee, so this probability is 0. And let's leave this thing to the up right corner. We'll use it later. Now it's time for us to compute n is 2. Bankrupt at the second cup means the price, total price of the first 2 cups of coffee is greater than 1. At the same time, the first cup of coffee is smaller than 1. Without doubt, S1 is definitely smaller than 1, so we can drop it. It means the probability of x1 plus x2 is greater than 1. Now we are going to use some knowledge in the conditional probability. This probability of x1 plus x2 is greater than 1 equals to this version, the conditional version, conditioning on x1 equals to some small x. This is some fixed value, small x, times the density of x1 at this small x. And I integrate this small x out. We should have seen this formula in the conditioning part of elementary probability. If you haven't seen this kind of formula before, believe me, this is true. Now we can plug in this capital X1 equals to some fixed number, small x, and also recall that x1 and x2 are uniformly random variables on 0 to 1. So we can plug in the CDF of x2 and the density of x1. We can get some formula like this, and we can compute this number. It is half. We also leave it in the corner. We will use it later. Now it's time for the n is 3 case. This one is a little bit more complicated, but the general idea is very similar to what we have done before. Bankrupt at the third cup means the sum of first 3 cups of coffee is greater than 1, while the first 2 is smaller than 1. Otherwise, we are going to bankrupt at n is 2 instead of 3. Now we denote the sum of x1 plus x2 as y, or we define this thing as something called y, and we also use the conditional probability formula for this y to get some inequality like this. This is exactly the same thing we did in the last page. We use this conditioning probability to compute the unconditioning probability. Note that the integral upper limit at 2, because the y is the sum of first 2 cups of coffee and it takes value from 0 to 2. So that's why the upper limit is 2. Now, we plug in the capital Y equals to some fixed number, small y, and we also split this integral into 2 parts. One of them range from 0 to 1, and the other of them range from 1 to 2. Why am I doing so? Because let's focus on the second term. In the second term, the range of small y is 1 to 2. But here, we also require the small y. In the probability, we require the small y to be less than 1. Just like the number 1.5 is smaller than 1 is impossible event. So this event is impossible, which means this whole term is 0. We don't need to care about it at all. We drop it. Now it remains to compute the first term. Let's recall that x3 is the price of the third cup of coffee. It is uniformly random on 0 to 1. So we can get some formula like this. We just plug in the CDF of x3. Now the thing is not completed yet because we haven't computed what is the density of y, the capital Y. Now let's remove all the redundant things and let's focus on y. Let's focus on the CDF of y. Remember that the capital Y is defined as x1 plus x2, capital X1 plus x2. We also use the conditioning trick to compute this probability. Now we condition on capital X1 is some small x. We use the same formula again. We can plug in this fixed small x and the uniform condition of capital X1 and X2, we get some formula like this. And here is something we need to pay attention to. The integral needs to be on 0 to 1. However, when this term y minus x is negative, this is possible because y is some number we fixed in the beginning and x ranges from 0 to 1. If x is greater than this small y, then this term may be negative. But in this case, x2 is a price, is a uniformly distribution on 0 to 1. This x2 is smaller than a negative number won't happen because we require x2 is a uniformly distribution. So we can further shrink our integral from 0 to 1 to be 0 to y, because when small x exceeds y, the x2 is required to be smaller than some negative number, and this is impossible. The probability is 0. We just ignore it. Now we can finally use the uniform distribution of x2 to get some formula like this. We directly plug in the CDF of x2 and it results in the answer like this. And of course, the density of y is just small y. Now we can finally plug this thing back to what we want to compute. After a little bit computation, we can find this number equals to the 1 factorial times 3, and we take the reciprocal. You might be confusing, why am I using this factorial here? It looks stupid, it's just 1, but we will see the answer later. Okay, let's leave this term to the corner, we will use it later. We also leave the other term, this term, in the other corner because we are going to use it later as well. Now it's time to compute the probability of bankrupt at 4th cup of coffee. You may wonder, if I continue to do this, we're going to compute countless number. But trust me, this is the final one we are going to compute. Bankrupt at time 4 means the sum of the first 4 cups of coffee is greater than 1. At the same time, the sum of first 3 cups of coffee is smaller than 1. Otherwise, we are going to bankrupt at time 3 instead of 4. Now, this time we set y to be the sum of x1 plus x2 plus x3. We use the same y for a different value now. Similarly, we use the conditioning probability formula. Now we also condition on y, but the y is something different now. We're conditioning on y, and we use this conditioning probability formula to compute the first line unconditioning probability. And similarly, inside the probability requires the capital Y is smaller than 1, so we can shrink the integral range from 0 to 3 to be 0 to 1, because otherwise the probability is 0. After we plug in this capital Y equals to some small y, we can now use the uniform distribution of x4. Remember, x4 is also uniformly distributed, and it equals to something like this. And again, we have to compute the density of y. Remember, this time the y equals to the sum of first 3. And we also use the conditioning probability formula. This time we condition on capital X3, and we will end up with some formula in this form. Remember that x3 is uniformly distributed on 0 to 1, so this term is 1. And further, because this small y minus small x cannot be a negative number, otherwise this probability is 0, so we can shrink our integral limit from 0 to 1 to be 0 to y again. This is a trick we have used previously. And now the density, or the CDF of x1 plus x2 is waiting for us in bottom right corner. So we can plug it in here, and finally we will end up with the answer y cubed divided by 3 factorial. And also the density of y is y squared divided by 2 factorial. Now we plug in again. We're plugging it into something we want to compute. With a little bit computation, we find this answer is 2 factorial times 4, and we take reciprocal. Now we can summarize. We list all the computation results here. After observation, we may guess the probability of n equals to k is k times k minus 2 factorial, and we take reciprocal. And finally, it's my time to say that I leave this as an exercise for you. This is what mathematical professors like to do, but this is just mathematical induction. We can do it very straightforward. I cannot say it is easy, but it's straightforward. And now we can go back to our final goal, to compute this expectation. We plug in everything we have computed, and after some simplification, we can find this thing equals to the summation of the reciprocal of k factorial, and use a little bit mathematical knowledge. We know this number is e, the natural logarithm, approximately 2.718. Finally, we're done. Now let's back to our question, how many cups of coffee we can have in this setting. And we have already computed the answer is approximately E. Don't forget to minus 1, because we cannot afford the last cup of coffee. The last cup of coffee is the one leads us to bankrupt, so we cannot afford it. And the final answer is 1.718. So this is how many cups of coffee I can afford on average. Before I end, I have some challenges for you to think about. One of them is this case. This formula, we have used it multiple times Sometimes we used it for x1 plus x2, sometimes we use it for x1 plus x2 plus x3. So a natural question is, for other distributions, unlike the uniform distribution, does this formula always hold true? And besides this formula, we also used another thing, which is after conditioning on this thing, we plug it in this capital X1 equals to some small x, and we compute the second line. The second line is something we really compute. But we plug in this capital X1 is small x. So the second question is naturally, given conditions, can we always replace random variable by some fixed value? Like something we did here, we replace the capital X1 by the small x. Can we always do this? These are two challenge and interesting questions for you. Before I end, I'm very willing to give you the answer. For the first question, the answer is yes. For other distribution, no matter it is discrete or it is continuous, you can always do something like this. But for the second question, the answer is it's not necessarily true. Under some condition or under some cases, we cannot replace the random variable by fixed value. There are some counterexamples. You can think of it. I think one of them can be constructed by normal distribution. So it's really interesting, right? And indeed, there are some points that are unclear to us in elementary probability. But believe me, all these questions will be solved in advanced probability or advanced statistics theory. So if you are interested, I'll see you there.